Okay, so our final speaker of the morning sessions will be Benjamin Knorr. Benjamin did his PhD in Jena and then had a postdoc here, which we remember well, then went to the Perimeter Institute and currently works at Nordita in Stockholm. So he is an expert really on functional renormalization group methods, specifically application to gravity. And he'll give us a, well, from that perspective, his view on scattering amplitudes and maybe a more non-perturbative realm of those and what one has learned in asymptotic safety so far.
Yeah, thank you very much, Renate, for this really kind introduction, and also thanks to all the organizers for having me here. It's really a very nice program. As Renate said, so I'm trying to give you a more non-perturbative view on scattering amplitudes, mostly from the perspective of asymptotic safety, but I think there are also some lessons or a blueprint for other approaches to quantum gravity. And I would like to start actually with a perspective on quantum gravity, because we are kind of all sitting in the same boat, right? We want to describe this elusive theory, and we have the same problem. We lack a smoking gun quantum gravity experiment. So having this situation, of course, sparks a lot of interesting ideas, big ideas, even bigger claims about quantum gravity. And we had this excellent talk by Bianca yesterday, giving us an overview of these different strands that are investigated. But now you can say, well, why should you trust my ideas? Why should I trust your ideas? So to phrase it as a provocative question, why should we trust any particular approach, right? It's all about big ideas at the moment. And I think this is a fair question eventually we all have to answer. And I would like to answer this question from my perspective by giving you a recipe for a falsifiable and predictive quantum gravity theory. Of course, we have to work out the details in practice, but at least this gives you the general idea, right? So it's a 3-step recipe, and I think the first step is, of course, fixing the theory. You have to define what are your symmetries, what do you want to describe? You want to describe gravity. You also want to describe matter in the end, the things that we observe in the universe. So it should at least include something like the standard model on the matter side. Now, once you have this theory, you've your base point, if you want, and from that theory, you should do computations, you should make predictions, and confront these predictions both with theoretical constraints, but also, crucially, with experimental data where you can. And I'm stressing here that it's really the simultaneous aspect that is really crucial here. Because, of course, we all have some free parameters in our models that we can tune and twist, and it's somewhat straightforward to get 1 or 2 specific things right in a certain model, but getting all of them right, or as many as possible, that's the real problem, I think. So once you're at that level, you can say, okay, at least I'm consistent or not in contradiction with collider physics, with cosmological evolution, with all these things, gravitational waves. Then I can think, or I can say that I have some trust in your theory. And only then I would say we can tackle the really big questions, like black holes, singularities, what happened at the Big Bang. Because then we have some trust that the theory is actually related to nature. And now you're probably not surprised that my tool of choice going through this recipe are gravitational scattering amplitudes. So this gives you a short outline of my talk. I'll briefly remind you a little bit about asymptotic safety. We had some excellent talks yesterday in one of the parallel sessions about this topic, so I'll keep that short. And then move on to the main topic of gravity-mediated scattering amplitudes, mostly with an asymptotic safety, as I said, but also with a little bit broader perspective. And then end with a short summary. Good. Asymptotic safety. What is it about? In its kind of simplest setup, if you want, the hypothesis is that metric gravity, as we know and love it, plus potentially suitable matter, like the standard model, as I said, maybe some dark matter, can be actually formulated as a quantum field theory consistently, but the kind of price that you have to pay is that you have to use non-perturbative methods. And how you should think about this is, or how we typically think about this, is in terms of a renormalization group. So as a very simple example, think of a theory. You have a single coupling, which is dimensionless, and you look at its RG flow across some energies, like Q squared is, Q is a momentum scale, so this is energy. Now, you all know asymptotically free theories where the coupling goes to 0 at very high energies. And the only difference in asymptotic safety is that the coupling doesn't go to 0, but it goes to a finite value at very high energies. Now, more precisely, what are the conditions for a theory to be asymptotically safe? Well, essentially two. The first condition is, as I just said, all the dimensionless versions of the couplings, more precisely the essential couplings, should approach such a finite value at high energies, and we call that a fixed point of the renormalization group. The second point is, of course, well, this is maybe just not enough because we want to have a predictive theory, right? It doesn't really help us a lot if all these couplings have to be fixed by experiment, because there are infinitely many of them. We do not want to have this situation. We want to have, let's say, 5 experiments, fix the 5 free parameters in our theory, and then predict all the rest from that. So this is, of course, also a crucial requirement for a sane theory. So this really sets the stage for the rest of the talk. As we know, at least at a fundamental level, perturbation theory for quantum gravity has its problems. You know, for example, the 2-loop counter term that we see that's the first non-subtractable divergence in GR. We expect more and more to come at higher loop orders. But I think we should not give up on QFT yet. In this talk, I want to zoom in a little bit and test asymptotic safety, at least, well, give you a perspective on how we could test asymptotic safety by connecting it to both theoretical and experimental constraints, and as I said, via the path of gravitational scattering amplitudes. And the whole underlying basis of this, or if you want my language, will be that of the quantum effective action, which is really the quantum equivalent of the classic action. It includes all quantum corrections. And this allows me to well, more or less straightforwardly handle all loop, at least in spirit, all loop orders. So with that out of the way, let me proceed to the main topic of this talk, gravitational scattering amplitudes. And we have to start somewhere, of course, and the easiest non-trivial example is a 2-to-2 scattering process. And this is also what I will focus on in this talk. So we have a mediated diagram and a contact interaction. Once again, since I'm working now with the quantum effective action, all these vertices and propagators are fully dressed, so they include all quantum corrections. This means that these are really the only 2 diagrams that you have to compute. Of course, for this mediated diagram, you might have S, T, and U channels, depending on the process. What are some benefits of this approach? Well, of course, you probe, in the end, quantum gravity effects if you look at gravity-mediated scattering amplitudes. But other really nice benefits are that there's, of course, this direct link to observables, as we just heard in the previous talk. Also, as we just heard, these are independent of arbitrary choices like gauge fixing, which, for example, in RG flow is not. And to reiterate again, since we are using the effective action, 3-level diagrams are enough to discuss this. Good. What's the general strategy for working with this from this viewpoint? Well, you fix the process that you want to investigate, and then you have to kind of parameterize the effective action, or at least that part that is relevant for this given scattering event. So you sit down, you think a little bit about the content of your theory, and what can enter basically these 2 diagrams here, right? So you have to control the propagator, a 3-point interaction, and a 4-point interaction. for this 2-to-2 scattering. The second step, of course, is, well, you need values for the couplings or the momentum dependence of these couplings, and you have to get it from somewhere. And the way that you would do this in asymptotic safety would be from the RG flow. But of course, if you have another method, lattice simulations, for example, you can substitute a step with that. And then, of course, you have these nice amplitudes. You get some, I don't know, 2-to-2 scattering amplitude. You can get cross-section from that. And then you have to ask the hard questions. Well, is it consistent with theoretical constraints, like unitarity bounds, causality bounds? And is it consistent or does not contradict experimental data? Disclaimers here. For now, I will not talk about external gravitons. This is just a really difficult to define object, what an on-share graviton is. You can, of course, discuss about that if you have any good ideas. And as in the previous talk, I will focus on the flat space-time and just standard asymptotic states, so really standard QFT scattering amplitudes. Because once again, we have to start somewhere, and then we can build up from there. So first step, parameterizing. And I want to be very explicit here. Let's take the simplest example of a scattering. It's scalar scattering, right? So I have two scalar fields, scalar field phi, scalar field chi, and I scatter them that two phi's go into two chi's. And I can do that either by gravitational interaction or by this contact term. So what do we have to specify to compute this amplitude? Well, we certainly need a graviton propagator here, once again, fully dressed. We need a 2 scalar 1 graviton interaction, and we need this 2 phi 2 chi contact interaction. Good. How does it look like at the level of the action? This looks a bit scary, I guess, but I will try to guide you through it. The first line really gives you the graviton propagator in flat space-time in full generality. So of course there's an Einstein term. I put the cosmological constant to 0 because we are working on a flat space-time. And then there are these two form factors, or what we call form factors. Think of them as just generalizations of some momentum-dependent couplings to curved space-time. They depend on well, the covariant Laplacian or the Lambertian, if you want. So you have these two terms, which are basically controlling the spin 2 propagator and the propagator of the conformal mode of the graviton. The second line is the action for, or part of the action for the scalar field phi. You have some generalized kinetic term, once again with a form factor. You can have a mass, for example, in there. And then you have these non-minimal interactions, two types, each with an own form factor, which now depends on 3 arguments, delta 1, 2, and 3, where the index indicates which field it acts on. So delta 1 acts on R here, delta 2 on the first phi, delta 3 on the second phi. You have a similar term with a Ricci tensor here. A very similar term to this, you also, of course, have for the field chi that it did not spell out here. And the final term is this contact interaction, which depends in total on 6 contractions of momenta, if you think of flat space-time. And of course, I want to emphasize here that these form factors, or what is really in there is the full momentum dependence, is of course key in any of these investigations, because we are talking about scattering amplitudes, and we are interested in high energies in the end to check something like asymptotic safety or unitarity. That's where the meat is, if you want. And let me also point out that we wrote a form factor toolbox, so a toolbox to deal with these very complicated objects some years ago. Good. Let's go towards the amplitude. Let me start with this first diagram, the mediated diagram. Once again, well, 3 lines of formula, so it's maybe not so nice, but actually it's super easy if you look a little bit about, if you stare on it. So it really splits into 2 contributions, a spin 2 contribution and a spin 0 contribution. The spin 0 contribution comes from the conformal factor, and the spin 2 from the actual like TT graviton, if you want. And then these two contributions split into different factors, actually. You get vertex factors, which come really from the vertices. You can see that. There's one factor from the left vertex, one factor from the right vertex. Same thing here in the spin 0 sector. Then there's the scalar part of the graviton propagator, which carries the momentum dependence of that propagator. And then the last ingredient is such a contraction factor, which kind of gives you the angular dependence in the spin 2 sector. It just really tells you that this is the spin 2 contribution, nothing more. S, T, and U are just the standard Mandelstamm variables. Let me point out here that this expression is gauge invariant. We explicitly calculated this in a gauged fixed manner, but all the gauge dependence drops out, as you can see. So you have to trust me here, of course, that it actually does. The second diagram, the contact term, well, it's pretty straightforward. It's just depending on this 4-point interaction evaluated on shell. So there's not so much that so many simplifications that you can expect here. Good. Of course, this is a very simple example, scalar scattering, but the same recipe can be followed for really any scattering event. So we did the same thing just last year for scalar photon scattering and also photon-photon scattering. We also wrote a book chapter recently, which is part of this handbook of quantum gravity, which is hopefully being published soon. What is still on the table are fermions and maybe also some Young-Mills. And of course, also building up on combined systems. As a side remark, there are some recent developments in the field of asymptotic safety that we are now able to treat essential couplings or distinguish essential from inessential couplings. Just to remind you, essential couplings are the combinations of couplings that actually appear in observables. Because, of course, at the level of the path integral, you can do field redefinitions. Field redefinitions do not change observables. So this will really give us a better handle on these amplitudes because you can choose certain field redefinitions which make your computations much easier. And as I said, there's a lot of progress right now happening. Good. Let's get into the more complicated step, the computing. Here I have to focus again on asymptotic safety because that's where my experience lies in. There's been a lot of work in the last roughly 10 years on the graviton propagator, and there was also a really nice talk yesterday by Manuel Reichert on some aspects of this. I think what we can say by now is that there's no additional modes in asymptotic safety besides the massless graviton. The spin 0, so the conformal mode, behaves quite a bit different from the actual spin 2 sector. And as Manuel showed yesterday, there are first efforts to compute really in Lorentzian signature, because usually in asymptotic safety, we have to also compute like integrals, and this is typically done in Euclidean signature. Beyond propagators, it's really getting tricky. At the moment, we only have a very limited information on the momentum dependence. There are some works, but really I think there's a more concerted effort needed. And of course, in all of this, this really needs cutting-edge computer tensor algebra and numerics. So you kind of win that it's non-perturbative, but of course, there's no free lunch compared to loop expansions. So somewhere you have to sit down and do the hard computation. To maybe illustrate one or two computations, I would like to pick out this paper together with Mark, where we computed the momentum-dependent anomalous dimension of the graviton propagator and the corresponding Faddeev-Popov ghost. So you can see the eta TT is the spin 2 anomalous dimension, eta 0 is the anomalous dimension of the conformal mode, and eta CT and eta CL are the transverse and longitudinal parts of the Faddeev-Popov ghost. And you can see that, as I said, the spin 2 and 0 behave quite differently. The spin 0 goes to 0 at high energy, whereas the spin 2 stays at a finite value. You can also see that the two modes of the ghost behave roughly similar. The second highlight that I want to make here is this paper, which was presented by Manuel yesterday, on where they computed the spectral function of the graviton. Good. In the 5 minutes left, I would like to talk about the remaining step, confronting with theoretical and experimental constraints. Let me start with the experimental constraints. Now, fortunately, right now, I cannot tell you a lot, at least at the level of the scattering amplitude, because we are just not there yet. What I can tell you is that there are some first insights directly from the RG flow. For example, you might know this prediction of the Higgs mass from about 15 years ago, or the post-diction of the top mass. On the theory side, unfortunately, once again, we are still in the process of getting something. This whole project, or this whole line of research, only started recently, so please stay tuned. But once again, what we could do so far is already promising. We could deliver a proof of principle that asymptotic safety can actually coexist with unitarity and causality. And that's quite non-trivial, because there's certain conditions that are a priori independent of each other, and you have to make sure that you can actually fulfill all of this. And it turns out that these form factors have enough enough freedom to cover all these conditions simultaneously. But what we also found was quite a bit surprising, that these unitarity and causality bounds kind of need specific relations between a priori unrelated couplings. And there are actually some indications that in asymptotic safety we find this, but unfortunately there's not enough time to talk about that. Good, so let me summarize. I hope that you agree that falsifiability is at the heart of natural science, and as a consequence, it should also be at the heart of quantum gravity research, at least as much as we can. In my opinion, scattering amplitudes are a very promising tool to probe quantum gravity, because they span both the theory constraints and the experimental data. The ingredients of these scattering amplitudes can be computed ab initio, for example, with an RG flow in asymptotic safety, maybe from Monte Carlo data. So there's not really a need to guess if you have a well-defined theory as your starting point. And once again, from my perspective, I think in asymptotic safety, we have some encouraging progress. The fixed point that we see is a very stable result. Also, once we look into the more involved computations with all this momentum dependence. And this also shows that we do have the technology to compute these correlation functions. So we're getting there, but of course there's no free lunch, so stay tuned. Thank you.
Yes, thank you very much. Before the almost free lunch, can I invite some questions? Yeah, over there.
Well, my question is perhaps a bit ingenious, but did you already try to calculate some loop corrections within this methodology?
Loop corrections, so at least one loop. What we're typically using is the functional renormalization group. So one loop exact equation, so one loop is built in. Of course, since we are talking about non-perturbative physics, we have to make approximations, and approximations are typically not along the loop order direction, but orthogonal to that. So at higher loop orders, there's not a one-to-one correspondence, typically.
We have one question on Zoom. Could there be off-shell gravitons emitted by Hawking radiation, and could their scatterings be analyzed?
Sorry, could you repeat that?
Could there be off-shell gravitons emitted by Hawking radiation, and could their scatterings be analyzed?
Well, I would say we can only measure on-shell physics in the end. At least in the scattering amplitudes, the external states are on-shell. So this is within this line of thinking what we can talk about.
Are there any further questions? Are there any further questions? everyone's ready to go for lunch. So thanks again for the speakers of this morning. Thanks. And